Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over Arrhenius acid-base reactions. These are often also called neutralization reactions, so let's get into this. So acid-base reactions are called neutralization reactions because acids and bases neutralize each other, and so we're going to go over a few examples. So a good example of an acid-base neutralization reaction is going to be HNO3, which is nitric acid, reacting with sodium hydroxide to form sodium nitrate and water. So whenever you have an acid-base reaction, it's always going to be the case, or almost always going to be the case, that water is formed, and then you got some sort of salt, especially if it's a strong acid, strong base situation going on, as we have here. So nitric acid is one of the strong acids, and sodium hydroxide is a strong base. So one of the other things you want to keep in mind is that the acid-base neutralization reaction follows the same procedure as a double displacement reaction. So if you remember from your double displacement reactions, there you had a substance AB plus substance CD, and then you had the ions on the outside come together, inside ions come together to form your products. So that's what we have here. So in this case, even though the acid, remember, acids are not going to be ionic substances, they are molecular substances, but when you throw them in water, they will ionize into ions, so you can treat them as if they were ionic substances. So then the H is going to be the H plus here. So that and the OH minus are going to come together, right? So this would be your AB. This would be your CD. And then, so the A and the D are going to come together, right? So here, this is going to be AD. Right, so the hydrogen and the hydroxide come together to form water. And then the inside ions are going to come together. So you got your sodium and your nitrate. Those are going to come together to form sodium nitrate. And so this is going to be your CB. Okay, so very much like a double displacement reaction. So let's break this down, what the reaction actually is actually happening in solution. So in your beaker that has your HNO3, your nitric acid, what's happening in the beaker itself is this reaction right here. So you don't have HNO3 floating around in there. This is a strong acid. So this is going to be basically 100% ionized in water. So what's going on in the beaker is that the HNO3 is going to donate, excuse me, sorry about that. So in the beaker, the HNO3 is going to donate a hydrogen to water, and then that's going to become your hydronium ion. And then what's left is going to be the nitrate ion in solution. So in solution, in your beaker of nitric acid, what you actually have in the beaker is a bunch of hydronium ions with your nitrate ions plus water. So that's what's in the beaker. So hydronium ions and nitrate ions, and because it's aqueous, you know there's water in there too. So don't forget about the water. So then in your beaker with the sodium hydroxide, that's going to dissociate into ions. So when you throw this into water, your NaOH, basically it is a strong base, so it's going to completely dissociate into its separate ions. So basically what you have in the beaker are sodium plus ions and hydroxide ions. So before you even mix these together, these are the ions you have in solution. So in your beaker of nitric acid, you've got these with water. In your beaker of sodium hydroxide, you've got these in that beaker with water, of course. So now what's going to happen when you mix these together? What you're going to mix all of these ions together when you mix them up. So before anything reacts, you've got all of this in solution plus your water molecules. Okay, with me so far? Okay, so you mix these together. Well, what's going to react? Well, your sodium ions and your nitrate ions, they're not going to do anything because as we as we learned from the other video on solubility of salts, we know that according to rule number 1, all group 1 metal ions are going to be soluble in water. And according to rule number 2, nitrates, all nitrates are soluble in water. So they're not going to form anything. So they're just spectator ions. So they're not involved. So we can ignore these. So the only other options, the only others that is the hydroxide and the hydronium ion. So the hydronium ion and the hydroxide ion are going to react. The hydronium ion is going to transfer hydrogen to the hydroxide, or another way to put it, the hydroxide is going to take a hydrogen from the hydronium, and then you get water. So if I write this out more clearly, you get H2O liquid plus H2O liquid. You get 2 water molecules. So this hydronium ion is going to give away hydrogen, so you get water left over. And then the hydrogen added to the hydroxide gives you another water molecule. So you get 2 water molecules out of this reaction. But wait, you're probably wondering, well, Mr. Koval, what's going on here? You have this plus this gives you 1 water molecule. How are you getting 2 out of this? Well, this is the reason. Notice we started with a water molecule here. So one of the water molecules here picked up the hydrogen to give you the hydronium. Now the hydronium is going to give that hydrogen to the OH minus, to your hydroxide here. And so you get that water molecule back. So the water molecule here is given back here. So you're really not producing a new water molecule. You're just getting back the water molecule you used here to get the hydronium ion. So that's why in reality, you're only producing 1 new water molecule. So that's why you only have 1 water molecule there. But in reality, this is what's happening in solution. So you want to keep this in mind. This is what's really going on in solution. The hydrogen from your strong acid is being donated to water to produce the hydronium ion. The hydronium ion is what is in solution. And then part of the reaction is where the hydronium ion gives that hydrogen to the hydroxide from the strong base, and that gives you another water molecule. Okay, I hope that's clear. So now let's look at how to predict the products of your acid-base reactions. So here I have a bunch of examples. And so again, you're going to follow the double displacement reaction procedure. So inside ions go together, outside ions go together to form your products. So here I have hydrogen, and then I have hydroxide. So if I do the inside ions together, right? So sodium is going to go with sulfate. And remember, when you put the ions together, you have to balance the charge. So sodium has a +1 charge. Sulfate has a -2 charge. So I need 2 sodiums to balance the -2. So then I'm going to have Na2SO4, and sulfates are going to be insoluble, are going to be soluble in water, unless there are those exceptions. But sodium sulfate is not an exception, so this is going to be soluble in water. Let me write this a little bit smaller. So this would be Na2SO4. It's going to be aqueous plus OH minus and hydrogen. Notice that I have two hydrogens here. I have two H pluses, and I only have one OH minus. So I'm going to need two of these to form water. So I have two of these. So I'm going to need two of those. So I'm going to end up getting two waters. But let me just make the one water. So hydrogen and OH are going to come together to form water. H2O, and that's a liquid, right? And so now I have my possible products, and so now I can balance the equation. So I have two hydrogens here. I know I needed two hydroxides to balance that out, so that should give me two waters. So I'm going to put a 2 there. And I have one sulfate here, and I have one sulfate there. That's balanced. And I have one sodium. But here I have two sodiums, so I'm going to need a 2 here. So now it's balanced. Now, that is my balanced equation for this reaction. So again, here, and again, you notice that if I have two hydrogens here, I need two of these. I need two hydroxides, and that's going to produce two waters. Now, if I have this acid, this is phosphoric acid plus NaOH. Again, the inside ions go together. So sodium has a +1 charge, phosphate has a -3, so I need 3 sodiums to balance the charge. So I'm going to need Na3PO4, and again, that's going to be aqueous because phosphates are going to be insoluble unless it's with a group 1 metal. Just like here, we have a group 1 metal. Group 1 metals, any ions with group 1 metals are going to be soluble in water, no exceptions. So here I have sodium phosphate, soluble in water, no exceptions. Okay, so that is one possible product. And then, of course, the hydroxide and the hydrogen come together to form water. And I've got H2O, liquid. Okay, so now I balance my equation. So I have 3 sodiums here. I only have 1 here, so I need 3 sodiums. So that's balanced. I have 1 phosphate here, and I have 1 phosphate there. That's balanced. I have 3 hydrogens here. Those 3 hydrogens are going to balance or combine with these 3 hydroxides to form 3 waters. So I should have a 3 there. So now I have a balanced equation. So that's it. Next, I have aluminum hydroxide solid reacting with HCl. Again, outside, inside. So here I have the outside ions coming together. Aluminum has a 3+ charge. Chlorine has a -1, so I'm going to need 3 chlorines or chloride ions to balance with the aluminum ion. So that's going to be AlCl3, and that's going to be aqueous because chlorides are soluble in water except for when it's silver or lead 2 ions. So this is going to be aqueous, soluble in water. And then the OH and H come together to form water. So here we have H2O, liquid. And now we balance our equation. So I have 1 aluminum here, 1 aluminum there. That's balanced. And then I have 1 chloride ion there. I have 3 here. So I'm going to need a 3 in front of there. So now it's balanced. I have 3 hydroxides, 3 hydrogens. That should form 3 waters. So I'm going to have a 3 there. Now it's balanced. Okay, now for these are tricky. You got to remember these. These are easy to forget about. So there are reactions called gas evolution reactions. You have to watch out for those. So in this case, you could be fooled into thinking that no reaction occurs when indeed there is. Also, you got to be careful with regard to the formation of gases. So here's an example. Anytime you have a carbonate or a hydrogen carbonate is part of your reaction with an acid, you're going to form a substance that can then further decompose and produce a gas plus water. So without any further ado, let's look at these two. So here I have sodium carbonate. We can do our inside-outside double displacement reactions like we normally do. So let's go ahead and do that. So here I have sodium carbonate. So the chloride and the sodium are going to come together. So that's going to give me sodium chloride, NaCl, and that's aqueous in solution. And then the carbonate and the inside ones, so hydrogen and carbonate going to come together. Carbonate ion is a 2- charge, and the hydrogen here is an H+, so I need 2 H pluses to balance the carbonate charge. So the formula there is going to be H2CO3, and that's going to be aqueous. So if we balance our equation, so I have 2 sodiums here, I need a 2 there. And then I have Cl here, Cl, I have 2 Cl's here, so I need 2 Cl's there. And then 1 carbonate, 2 hydrogens, 1 carbonate, 2 hydrogens. So it's all balanced now. Now here is the point or that you need to watch out for. So if you're not careful, you could see that, oh, look, I have aqueous here, I have aqueous here. So your conclusion could be that, oh, well, everything is aqueous, everything is floating around in water, no reaction. But you would be wrong, because this can break down into carbon dioxide and water. So with I'll write it up here. So the thing you got to watch out for is when you get this as part of your product, if you get, which is called carbonic acid, this can break down into water and carbon dioxide. So this will actually become H2O liquid plus CO2 gas. So in reality, when you mix sodium carbonate with hydrochloric acid, you should see bubbling occur. The bubbling is due to the formation of the carbon dioxide gas. So again, when you mix these together in lab, you should see bubbling, which is going to be a sign of a reaction. But if you look at your reaction here, you could be fooled into thinking no reaction is going to occur. So be careful of that. Same thing occurs here with sodium bicarbonate. So if you predict your products, again, your sodium and your chloride ions are going to come together, and you're going to form, again, NaCl, aqueous, plus, and then you have your HCO3 plus hydrogen. That's going to form, again, H2CO3, aqueous. And so if you balance, right, so sodium, 1 chlorine, 1 sodium, 1 chlorine, that's balanced. And then you have 1 CO3, 1 CO3, and you've got 1 H, 2 H's, 2 H's. So it is balanced. And once again, you should notice, hey, I have H2CO3, that's carbonic acid. Therefore, I would expect it to break down into water and carbon dioxide, gas. And so my products, my real products in the end is not going to be this, but it's going to be these two here. So you got to watch out for that. So I hope that this is helpful. If you enjoyed this video, if you learned from this video, then by all means, like the video, share the video, hit that like button. Also, make sure that you subscribe to my channel, hit that notification bell. When you do, click all so you can be notified by all the videos I put out. Finally, please put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you want me to cover, if you have a question or a problem you want me to help you with, please put it down below in the comment section. I would love to help you with those items. Thanks for joining me. Have a great day.